All right. Hello, everybody. For those of you just joining us this term and didn't have me last term, welcome to CS 251. My name is Nick. And I wanted to get started today by going through the course website, talking about sort of the structure of the class, and then we're going to jump right into chapter 6 of our textbook, right into the material. I did want to draw a distinction to begin between the two classes that are going to be here. So the course which was scheduled from 1 to 4, Monday, Wednesday, that's my remote class. And those of you that didn't have a lecture scheduled, but I emailed you and said, hey, you can join up at this lecture, that's my online class. Okay, so so you folks that are in the remote class, I was saying just before we started recording here, I have your web work set up already. The online class is not ready yet. I'll do that after lecture today, so it'll be ready this evening. So I just wanted to let people know that the web work, which is, for those of you just joining, that's the online homework system that you'll be using, which I'm going to show you today. It is set up for the remote class, but it's not yet set up for the online class. And maybe an hour after lecture today, I'll have that, finish getting that set up. So that's the deal on web work, to answer your question, Vivi. For those of you in the, yeah, you're welcome. For those of you in the remote class, if you would give it a try to log into WebWork and see if you can log in, your password works, you have access to all the problem sets for this term. If someone would do that and check and make sure that's all working, that'd be great. Just make sure I didn't screw anything up. That'd be cool. Okay, and while someone is doing that, let me jump into the course material. So hopefully all of you have learned Desire to Learn before. Has anyone not used Desire to Learn before? Okay, then I'll go rather quickly. So as usual, in the content section, it lists out everything that you're going to need to do in the class. So the class is 10 weeks long. It's all organized by week. And the numbers here indicate the sections that you'll need to look at for that week. Now, it's a little bit goofy because, oh, the web work works for you, David. Awesome. Thank you. It's a little bit goofy because there are two different editions of the book that you could use. You could use the 4th edition or the 5th edition, and the sections in the textbook are listed right here in each week. Right? So in week 4, you read sections 9.1 to 9.4. But that's according to the 5th edition of the textbook. I'll jump in and write some little notes on these for the differences if there's a difference in the 4th edition. I know week 6 right here, this is for the 5th edition because you're doing section 1.4 and 4.9 in here. That's the 5th edition. All of that material is still in the 4th edition. It's just in different sections. It's that material's on section 10.1. So it's a little bit, or not 10.1, 9.9 or something like that. Anyway, I'll look and annotate these guys for the 4th edition because the sections are a little different. But the point is, in each week, you can see which sections of the textbook you need to look at. If we go into a week, like week 3, for example, it's going to be the same thing every week, the same kinds of stuff, okay? So what you're going to have is a quiz to check your understanding of the reading. Quiz is not for a grade, it's just for practice. You can take it as many times as you want. It's just for fun, right? To see if you're really understanding things. Next comes the web work. Which I'll talk about in a moment. If you click on this web work link here, it takes you to this list. And for the remote people, your CRN is 20665. So you're this first class. The online course is 21720. So that's the second link. So I'll just give you an example. Click into this link and you can see it takes you to this list of all the problem sets. And you can see here that for web work in week 3, we do 8.1 to 8.4. Down here, you can see 8.1 and 8.2 are the only sections that have a web work component, okay? And those will be due on the 16th of April, and then reduce credit on the 18th of April. So you can see the due dates there. If you click into one of these, you can see there's 10 problems. Some have limited number of attempts, right? So these problems 1 and 2 have 3 attempts, but the rest of them are unlimited. So depending on the problem, you get different amount of tries that you get to do. So it's important to look at those before you just jump in and waste all your attempts and get the question wrong, right? And if we were to click on one of these, then it gives you the problem. It says, okay, there's a true and false problem. And you just put T's and F's in here. So I'm not even going to read it because we haven't learned this yet. I'll just put all true just to give you an example. Right? And then we'll submit answers. It says at least one of the above answers is not correct. We only got 40% for this problem. Well, since there's 5 questions here, right, that means that you got 2 out of 5 correct. And then it's your job to go figure out which one you got right and which one you got wrong, and go back and fix your answer to try to get the best score possible for the question. Yeah, it's exactly the same as CS250 if you had me for CS250 last time. Yeah, exactly the same setup. If you're new here and you have questions about this, please feel free to jump in and ask questions at any time. I'm always happy to take questions. So please don't worry about interrupting me. Just go for it. Feel free to hop on the chat and ask questions. Feel free to hop on the mic and ask questions. Please don't worry about interrupting me. I would much rather be interrupted than have you be confused, right? So that's the web work, okay? So let me move back up the stack here, back to our content, okay? So there's a quiz that I told you about, right? Take as many times as you want, it's not graded. Web work, sometimes the problems have a limited number of attempts, sometimes they don't, depends on the problem, but that will be for a grade, okay? So you go over into this homework system, and the nice part about web work is it gives you immediate feedback, right? You don't have to, email me a photograph of a sheet of paper and wait a week for me to go through and grade it, right? Instead, you get instantaneous feedback, which I think is really nice and helpful when we're trying to learn a bunch of math really quickly, right? These practice problems right underneath the web work, those are not graded, okay? So those are in your textbook, and they're just for you to cement your understanding. So, at the end of each section in your textbook, there's, a list of problems, just like, like most math books, right? At the end of each section. And here are some recommended, sort of recommended reading, right? Recommended practice problems that you could do. I would recommend if you have extra time to try to blow through as many of these as possible. They will help round out your understanding of the material. Now, again, they're not graded, so if you don't have time, don't do it, right? Focus on the things that are graded. But if you do have time, that would be a smart thing to do. Okay, so what else do we have each week? We also have a proof and a collaborative proof. Now, they're the same sorts of thing, okay, but they're graded differently. So let me give you an example here. So if I go to the proof, and it has this little document here, which I'll open for you. All right. So each week, there's going to be 1 graded proof and 2 collaborative proofs, okay? Now what you're gonna do is you're going to write down a mathematical argument that demonstrates the truth of the sentence here, okay? So here's a sentence. R and S are relations on a set A. If they're both transitive, then their union is transitive. And you need to make a mathematical argument as to why that is true, okay? And what you're gonna do is you're gonna write down that explanation, that argument, on paper. Or if you like, you can create it in Microsoft Word, or if you're feeling fancy, you can use LaTeX, which is a mathematical typesetting computer language, okay? Any of those are fine. And you're going to send me your argument in the assignment Dropbox on D2L. So let me show you where that is. So over here in assignments, you see there's proof 1, proof 2, we were just talking about proof 3. So you would go into the proof 3 Dropbox, and most people will be writing with pencil and paper, take a picture with your phone, and then send me the picture, and that's your homework, right? So you'll be turning those into the proof 3 assignment Dropbox in week 3. In week 1, you put it in proof 1, of course, and so forth, right? The collaborative proofs are a little bit different. That's Luna, you can hear in the background. She'll be interrupting us the entire term, as she did last term. That's my dog. So then if we go back, and let me show you the collaborative proofs here. So here's 2 other things that you need to prove, right? Sort of like in a court of law, right? You want to prove that someone's guilty, right? You need to make an argument that proves beyond a shadow of a doubt that they must be guilty. You're doing the same thing here, except instead of law, it's math, right? So here, these two collaborative proofs, you have this set of points and you have this relation that's defined by division, and you want to show that that's an equivalence relation, which we'll learn all about what all that means in a couple weeks. Right? And then there's this other question, which is a similar sort of thing. Again, you're proving that something is an equivalence relation. Now, for these collaborative proofs, what you're going to do is you're going to put them in a different spot. Okay, you're not going to put them in the Dropbox. You're going to go into the discussions forum. And you can see here in the discussions, you're going to introduce yourself, and here's some general comments and questions. But then you have the collaborative proofs. Okay. And you can see here, there would be collaborative proof 3. So you would go into here, you're going to make a discussion post, and again, you're going to have pencil and paper, written notes about your argument as to why the thing is true. You'll make a discussion post and attach pictures to your discussion post. Let me give you an example of how to do that. And so if I want to make a discussion post, say, here's my answer, attached, oh boy, attached. And you scroll down, you can add a file to your post. So that's when you would go to your computer and upload whatever photographs you'd taken or Word documents or LaTeX documents you've created of the answers to your proof. So maybe it's called proofs. This is the question document, so don't do this, but you choose a file, whatever it is, then add it and post your discussion post. Now, the way that that's going to work is you won't be able to look at other people's posts until you've posted your own thing. So you can't just go on the discussion forum, look at what someone else did, copy their work and turn that in. That's not going to work, right? Instead, you go off and do your proof, make your post on the discussion forum. And then once you do that, it'll unlock everyone else's posts so that you can go through and see what other people's arguments look like. Right? So that's why it's collaborative, right? You all get to see how other people made the argument, and there's always many different ways that people prove things. There's lots of different, ways of approaching the answer. So I think it'll be quite useful for you guys to, after you submit your own collaborative proofs, go through and look at everybody else's. And sort of get a good idea of the different approaches you could have taken to the problem. Or, if you had no idea what you were doing and your answer was totally wrong and made no sense, that's fine. Then you go on and look at other people's and find someone's, who knew what they were doing. And then you can, learn and see, what the right approach was. So it sort of, I think it fosters a nice sense of community amongst you guys to be able to look at everyone else's work and say, oh, well, this is how they did it and this is how they did it and so forth. So the grading of the proofs is something I should mention. The graded proofs will be out of 10, right? So you can get partial credit. So with the graded proofs, I'm going to actually be looking at, did you get it right or wrong? Okay, and there's one of those per week. So I'll actually read through it and say, okay, well, you got this part right, this part wrong, and maybe you get 8 out of 10 or something like this. For the collaborative proofs, I'm only grading it on binary scale. Did you do it or not, right? If you made an attempt at the collaborative proof, you'll get full credit, right? So I'm not going to be grading those in detail. The idea is, instead of me grading it and you looking at my notes, you're going to go through and look at other people's proofs to try to see what other people did, rather than me telling you what the right way was of doing it, right? So there's two sort of different, approaches for learning going on here, which is what I'm trying to do. I'm trying to give you guys different, appeal to different learning styles, right? One last thing is the lab. Okay, so we're going to be doing some labs with computer graphics this term, just like last term. But this term, we're going to be doing 3D laboratories instead of 2D, right? So we're still going to be doing computer graphics, but now we're going to be doing 3D graphics, which is going to be a bit of a step up. So hopefully that all goes well. I think people, I just read my course evaluations, and quite a few people said they really liked the labs. It was like their favorite part of the class last term. So I think that you'll continue to enjoy these this term. It's kind of a nice break from, the thousands of lines of algebra that you'll be writing down, right? Instead, you'll get to make a fun 3D shape with computer graphics. It's kind of a nice break, I think. Definitely fun. Yeah, awesome. Okay, so that's our week. That's what our week looks like. Let me do a quick overview. Okay, so on the weekend, you're going to do the reading for the chapter. okay? And probably try to take this quiz, okay? So you'll be doing that the weekend before lecture, okay? So Saturday and Sunday, you'll do the reading and take the quiz. On Monday, you'll come to lecture, okay? And we'll start going over the material from the book. Lecture is going to consist of me doing problems with you. That's all we do. And the lab, we'll go over the lab assignment for a little while. But you didn't follow the web work. Oh, yeah, Luan. So you're in the online class and that doesn't have the web work set up yet. So I'm going to do that right after lecture and then it should work. Yeah, so I did know that. Yeah, cool. Okay, so yeah, you're welcome. So, okay, so over the weekend, you read the chapter, then and do the quiz. On Monday, you come in, we do some practice problems. Then you guys start in on the web work, right? You do the web work stuff between Monday and Wednesday. On Wednesday, we have lecture again. And so, you know, you'll come back, you know, whatever web work problems you didn't understand, if there are any of these practice problems here that you didn't understand, you'll come, you know, with questions on Wednesday. And we'll work through all your questions, finish up the reading. And then on Wednesday, we'll also go over the lab assignment, okay? Then your proof, the collaborative proof, the graded proof, and the lab, and the web work, everything is due on Friday at midnight, okay? Friday at 11:59 p.m. So Friday night, Saturday morning, right? And everything is going to be due all at once, okay? After everything's due for that week, it'll be Saturday again. You'll then start in on the next set of reading and the whole process repeats. It's a big for loop, right? So that's sort of the schedule or layout for the term. Let me ask you this. Does anyone have a huge problem with having, you know, a lot of work due on Friday? Is that disastrous for someone's schedule? If so, now is the time to say so. Going once, going twice. Yes, that is disastrous for your schedule, Jen. Okay. Would it be helpful if it was Saturday instead of Friday? Sunday's too late because then you don't have any time to do the reading. So that's Sunday's not an option. Yes, you are allowed to submit before Friday. Yep. You can go ahead if you want. Absolutely. Yeah, I mean, you can do the whole course in a week if you want to. So Jad, would Saturday be helpful or Saturday wouldn't help? Or could you get it in on Thursday perhaps? Or let me ask this. Saturday would help you a lot, Amber. Another course has Friday due dates. Okay. Okay, yeah, I'm happy to switch it to Saturday. That's not a big deal. So the question is between everything due on Friday or everything due on Saturday. Let's have a vote. Okay, so if you would type in the chat window, Friday or Saturday, or nothing if you don't care, then we'll take a vote. Okay, Saturday. Ooh, any Fridays in the crowd. Everyone likes to procrastinate, I know. If it was me, I would say Saturday too. Okay, so it looks like anyone who cares wants it to be Saturday. So I'll switch everything to Saturday. No big deal. Okay. Now at that time, you're only going to have one day on Sunday to do the reading. So hopefully you have, you know, keep some. It's not procrastinating; it's time management, right? Exactly. So yeah, so hopefully, you know, you'll reserve a few hours on Sunday to get through that reading, because if you come on Monday to lecture without having done the reading, you're going to be lost during lecture. And I think some of you guys can attest to that from last term, that if you come to lecture without having done any prep work, it's not as useful as if you did a little bit of work prior. Would you all agree with that? I mean, that was my impression, but let me hear from you guys. Does that sound right? For sure. Okay, cool. All right, so I really do highly recommend doing the reading on Sunday, even though you just spent all day Saturday finishing everything because you waited till the last minute, right? So your weekends are going to be busy, and that's fine. You know, whatever works for you guys, I'm happy to do, right? So, okay, so things are still all due on Friday right now because that's how I set it up. So it's going to take me a day or two to fix it all, but everything will be due on Saturday this week and throughout the rest of the term. So no worries there. Okay, cool. So, Great. So we went over the content. You can see the content in each week lists out all the things you have to do, has links to everything and all that good stuff. So let me pause here for a moment. Does anyone have questions before we start going over the syllabus? What do you guys think? Okay, cool. One more thing I should mention is that you can turn in late work. So everything will be due on Saturday, but you can turn in the web work on Sunday for half credit, right? So if you can't finish everything up on Saturday, leave the web work till later because at least you can turn it in late. The lab and the proofs, you want to get those done in time because I will be less likely to give you, in some cases, I'll let you turn in some late work. But if you have a choice between the two, get the web work done because I'm sorry, get the proofs done. And then the web work you can do for, you can do for one extra day for half credit on Sunday. Right? All right, cool. So with that, let's jump into week 1 and talk about the syllabus. All right, so you are at PCC. You are in CS251. The CRN is different for the other class. It is the spring. We will be meeting 1 to 4. I am Nick. You can call me Nick, Professor Ensalada, hey you, whatever you want. I don't care. I'm not the kind of guy, not the kind of professor that's really super into my name. I think it's kind of weird and egotistical. Call me whatever you want. My office hours, that's an important one. That'll be in the hour before class, right? So so from 12 to 1, I wasn't here today because I'm trying to get everything all together. But for every other class for the rest of the term, I'll be here for the hour before class. If you all want to jump in to it'll be the same Zoom room. So the same place where we're meeting for class. I'll just be there an hour early and you can pop in and ask questions on the, web work, proofs, whatever you have questions on, lab stuff, whatever it is, right? So my office hours will be in the hour before class, same Zoom room. Course description, we're going to learn about combinatorics, functions, relations, recursion, regular expressions, probability, efficiency of algorithms, graphs, regular expressions, and finite state automata. In other words, we're going to do the entire second half of the textbook that we started last term, right? So we're going chapters 6 through 12. We're doing the whole shebang. We're going to skip a section here and there, but we're going to do all the remaining parts of the book pretty much. Speaking of which, that book that I just mentioned, let me do one of these and one of these. For those new people, you get to see my fancy overhead camera that I took from PCC. It doesn't look that fancy now. There we go. That's better. This is the textbook. Discrete Mathematics with Applications. I have the 4th edition because with the 5th edition, they don't give you a binding on the textbook. It's just like a vacuum sealed pack of paper sheets, which is total garbage. So I still use the 4th edition because it's the only one that has a back. And as you can see, it's kind of falling apart, but you do what you do. Either the 4th or the 5th edition will be fine for this course. Those practice problems I was telling you about earlier. So here's section 6.1, right? Section 6.1 here. You can see there's some test yourself and then exercises. And you can see there's all these different exercises, practice problems. Those are from that list of practice problems under the web work link in the content. That's where you go and find those. There's in the textbook at the end of each chapter section. Kobe has a question. Can you join the Zoom room even if you don't have questions? Oh yeah, sure. Yeah, you can join up anytime you like. Oh, the other thing that I should tell you is that there's another Zoom room if you all want to get together with your classmates. Now there'll be separate ones for the remote section and the online section, but it's the same idea. Y'all can't go in each other's rooms because you all have different desire to learn shells. So you can't really join up with the other class unless you email each other and make your own Zoom meeting or whatever. But for those of you in the same class, if you go to online rooms, And you can see here, there's this recurring study hall. If you want to meet up with a couple of people and work on the proofs together, something like that, that's totally fine. Here's where you would meet in the study hall here, which is just open for the duration of the term. There's no like times that it's open. It's just open 24/7. So you would join up here if you want to hang out with your classmates and have a Zoom meeting and talk about the course and do problems together. So that's where you do that. Great. Okay, so let me go. I lost my syllabus here. Let me go back. Okay, so that's office hours, the textbook, study hall. What else we got here? Okay, homework. Great. You should probably allocate several hours each week to work on homework. Well, let me ask you guys. So last term, on average, how many hours would you say you spent on homework, including labs, proofs, and web work? Does someone want to give me an estimate of the number of hours per week you were working on that? Maybe a few people could, because it takes different people different amounts of time, right? So what would you guys say? 7 hours? You logged it, Lucas? Wow. 3, okay. 5 to 8, okay. So we'll say 5 to 10 hours, right? So we'll say 5 to 10 hours a week on homework, which is a lot, right? In addition to 6 hours of lecture. So, total, we're talking 15 hours a week maybe that you're spending on this class. That's a lot, right? That's almost a part-time job. So be careful here. There's going to be a lot of things to do. This is a very intense course with a lot of difficult mathematic material. And so, if you're trying to work a full-time job and take a full load at PCC right now, this might not be the best time to take this class. Talking about time management, like, yeah, you can probably like scoot your way through and get a C and pass, doing a lot less, right? But, if you're trying to transfer to Portland State and you need this class to get there, which probably is why most of you are here, then you're going to have that minimum GPA. And if you don't have enough time to allocate, you might not make that minimum GPA. So, I realize that there's, you're between a rock and a hard place, right? You need this class to transfer and you want to transfer in the fall, and you're working full time and, and you're screwed. And that's life. Like sometimes that's the situation. But if you're taking this class without, this sort of strict time schedule and you really don't have the time to allocate to it this term, I would recommend waiting until you really have the time to dedicate to the course, because it is a very difficult class. Luan, I wouldn't say it's more difficult than last term. I would say it's about the same. It's just about the same as what we did last term. I tried to make the classes, as close as I could in difficulty. So. But then again, I will be assuming that you know how to do proofs now, right? Because we spent a whole quarter working on that. So I'm kind of going into this with the assumption, okay, now you can do proofs. And for those of you that didn't have me last term, hopefully when you took CS 250, you did some proofs. So you sort of have an idea of what we're doing there. Well, let me ask this. Does anyone like not know how to do a proof, has no idea what I'm talking about with proofs, and is very worried, as you should be? It's been a while. Okay, well, that's okay. It's, it's like riding a bike, that's no problem. You're a little rusty. Okay, yeah, that's all fine. So long as you have some idea of what I'm talking about, that's all I'm really getting at. And of course, we'll be doing a million proofs as we go through lecture and all the, practice problems and proofs and all that. So, so don't worry too much about that. So long as you have some sort of familiarity with the idea. Okay, so that's homework. Right, lab work, we talked about that. Proofs, we talked all about those. It's the same number of proofs as last term, Raphael. So 1 graded proof and 2 collaborative proofs each week. So it's the same amount. Yeah, good question. Okay, late work, as I said, you can turn in web work problems. Well, this said 2 days late. Now it's 1 day late if we're gonna have everything due on Saturday, right? So 1 day late for half credit. And I may accept late proofs or labs at my discretion. So if you need to, turn something in late, come to office hours and talk to me and we'll, we'll figure that out. Attendance. Coming to class is essential in succeeding in the course. However, I can't grade you on attendance because of COVID and the new PCC policy. So this is wrong because it's from last year. Let me go through and fix it. So attendance will be worth 0% of your grade. However, it's absolutely essential that you come here. or if you're watching this as a recording, it's essential that you continue to watch the recordings. And I should pop that 5% back into, oh boy, I guess proofs is probably where it should go. Okay, so now that adds up to 100, right? Yes, okay, good. Okay, so attendance will not be graded. However, it is arguably the most important part of the class. I will award grades as follows: 90, 80, 70, 60, the usual grading scale for A, B, C, D, F. Deadlines, you can drop this class up until Saturday of this week. You can withdraw from the class up until Friday of week 8. If you want to change over to pass, no pass, that's fine. You can do that. I don't remember if that's kosher with PSU if you take it pass, no pass. I seem to remember that there was a new COVID rule where you could take courses pass, no pass, and PSU would still count it. But don't quote me on that. If you want to change it, go double check with PSU first. But I seem to remember hearing something about that. So if you want to take it pass, no pass, definitely go talk to your transfer institution and make sure that that's cool before doing it. All right, cheating and plagiarism. Okay, so you can work together on things, and I encourage you to work together on things. Okay, so web work problems, the proofs, the labs, anything in the course, except for the exams, except for the midterm and the final, those I expect you to do by yourself. But anything else in the course, any of the weekly work, I encourage you to work in groups. Okay, now what do I mean by that? I mean, you go on a Zoom meeting, or if you got your vaccine, meet up in person, I guess, and hang out and work on the problems together. Now, you're welcome to do that, but I do need different submissions from each person in your group. Okay, so if you want to, go talk about proof 1 in the study hall this week, great. Grab a couple of people. Maybe you have some study buddies from last term. You want to hang out with them. Awesome. If you're new this term, then make a couple of friends, make a study group. That'd be great. But I do need each person to turn in their own unique proof at the end of the day, right? So please don't, Raphael, please don't, work with Luan and then take a picture of Luan's work and say that that's yours. Don't do that, right? Everyone needs to, submit their own separate work, although it's totally fine if you, analyze the ideas as a group beforehand. Does that distinction make sense? Is everyone cool with that? Yep. All right, cool. And as I said, the exams you'll take alone, okay? So that's that part. Disability. Okay, if anyone needs disability stuff, just let me know. Happy to give you extended times and all that. I will not discriminate against you for any reason. Well, I can put it this way. I couldn't discriminate against you for any reason because I'm a numbers kind of guy. Okay, this is a math class and I'm a math guy. So whatever grade you get is going to not be based on anything about you except the scores that you get on your assignments. Okay, so there will be no possibility for me to discriminate in any way. Not that I ever would, because that's a horrible thing to do, but I couldn't, no matter what, based on the way that I do my grading. And so along those lines, if you're really nice and polite to me during lecture, it's not going to get you a better grade, right? I'm just going to grade you on, I'm just going to add up the numbers and do the percentages, and that's what you get. So I wanted to alert you to that. You can read about PCCs at Sanctuary College, okay, and flexibility. So I can change whatever I want all the time, right? But I will only make your life easier. I will never make it harder, okay? So just like we said, okay, instead of homework being due on Friday, now it's gonna be due on Saturday. Great, I'm happy to change things, okay? But I'm never gonna give you like an extra assignment during the week. I'm never gonna say, oh, instead of due on Saturday, this is due now 3 days earlier. I'll never do that to you. I'll only cancel assignments if there's a, some natural disaster and we need to cancel class, or if my electricity goes out for no reason, which it has done in the middle of lecture before, then maybe we'll have to cancel one of the assignments for that week because we didn't have time to go over the material during class, right? Or I'll push back a due date or something like this. So I can change things, but I'll only change them to make your life easier. All right. Does anyone have any questions about the syllabus? I'll let you think about it for a minute. Okay, cool. Then let me pop over to WebWork for a second. There's one more thing I forgot to tell you. For your homework sets that you're working on, if you would please start with the orientation set, especially for those of you that haven't used WebWork yet, that didn't have me last term, and go through these problems. They're going to explain how WebWork works. Okay, so if you go through all these orientation questions first, there will just be, some like this one. It's learning how to use the Ask Me for Help button. There's an email instructor button below, right here, email instructor, right? So if you ever have a question on a WebWork problem, if you use this button, what it actually does is really fancy. It sends me your particular WebWork question with your history of all the answers that you've put in, and you can write me a little note with your question in it, right? So I'd much prefer if you use this button rather than just shooting me an email saying, oh, I don't get number 8.1.7, right? I don't get that question. And shoot me an email on PCC. You can do that, it's fine, but it would be nicer if you use this button, because then it sends me a link to that particular question, so I don't have to go log in and everything, right? It just sends me a link to that question and shows me all your prior responses and shows me your question all at once. So it's really convenient for me. So if you would use this to email me about WebWork, that would be great. And that's just one example of something you learn about in this orientation homework set. So if you would do that one first, that'd be great. And then, jump into the chapter 6 material afterwards. I know these are kind of in a weird order, but the orientation should come first. Okay, cool. And that's all about WebWork. I think that's all I want to say. There is a lot that we need to talk about for the lab assignments, but I'm going to do that on Wednesday because I don't want to spend, an hour and a half today talking about boring crap, because that was all very boring. So I'd like to do something a bit more fun. Well, more fun for me anyway. I don't know if it'll be more fun for you. We'll see. But let's do some math, shall we? Let me get to the right spot here. Okay. Stop that guy and start video. Wunderbar. All right. So, chapter 6. Let's get started. We're going to talk all about sets, set theory. Okay. So let's begin with a simple question. What's a set? What do you guys think? A group of things. Yeah, a collection of things, elements, items, right? And usually that collection of items has some sort of common property amongst the items. So for example, you could have a set of colors, right? So you could have colors is, red, green, and purple, right? Or you could have a selection of people. Let's see, we've got Sean, Kobe, and Nick. Right? So generally what happens with these collections is there's some sort of common property that's shared by the items in the collection, okay? So this has the common property that they're all colors. This has the common property that they're all people, right? And you could make a set with a bunch of items that don't share any common properties, but that would be kind of a stupid set, right? So here's R for my random set, which has Honda, Nick, and purple. Right? There's a car, a person, and a color, and it doesn't really mean much anymore, right? You sort of lost the whole point of making a set in the first place, right? Now, generally, when we talk about sets in this course, we're going to be talking about sets of numbers, okay? Because we're in discrete math, so we're going to be doing these numeric sets. Now, the way that I've listed these sets here This is called set roster notation. And what that means is just like a roster, you know, in your class, right? If I was going to do attendance, I would look down the roster and read out everyone's name, right? Now, that's just a list of all the people that are in my class, just like this C is a list of all the colors in my set. So you know, make a list with, you know, comma separated items surrounded by curly brackets. That's the notation, right? And you list everything out that's in the set. But there's also a different way of talking about sets, which is called set builder notation, right? So I could say I have some set, which is the x's in the natural numbers such that 0 is less than x is less than 10, less than 5. Make it a little smaller. Right? Now this is called set builder notation. And the way that it works is you have a domain and a rule and the such that symbol, which is the pipe. Okay. And this is called set builder notation. This whole thing. Set builder notation. And if I wanted to translate this from set builder notation into set roster notation, what would be the roster of elements that would be members of this set? Good. 1, 2, 3, 4, right? 1, 2, 3, 4. Excellent. That again would be set roster notation. Yeah. Okay, so there's two different ways of talking about sets. Cool. Oh, I guess instead of rule, your book calls this a property. And say P of X for some property. I call it a rule, you can call it a property, same idea. Okay. So next we're going to talk about subsets. Okay. So what's a subset? A smaller set that belongs to a larger set or is contained in another set, right? A subset of a set is a smaller set contained in a, like, not the, I'll say a larger set. So for example, could you give me a subset of the set S? The set 1, okay? So the set 1 is contained in the set S. And this means subset, right? Similarly, the set 2, 3 is contained in the set S, right? Now this means a proper subset, right? This is a proper with just the C. What if I was to have the entire set S, 1, 2, 3, 4? And I say that's contained in S. Is this a true statement that 1, 2, 3, 4 is contained in S? No. How do I modify it? How do I change this to make it a true statement? You need the underline. Good. It's sort of like a less than or equal to. You can't say, you know, you can't say 4 is less than 4. That's false. But I can say 4 is less than or equal to 4. And I put this little underline under the less than, and now that becomes true, right? It's the same thing with subsets, right? If I have some smaller collection that's in the bigger one, that's a proper subset. But if I have the exact same collection, Well, that's not a proper subset anymore. It's just a regular old subset, right? So just a regular old subset could have all of the items in the original set. So I guess a subset is a smaller or equal to set contained in a larger set. A proper subset, and let me give you the symbol, that's this guy, right? A proper subset is actually smaller, or maybe I'll say must be smaller. And that's just the C. C for containment, right? That's how you can remember the little C there. C is short for contains, or I should say is contained in, right? So the set 2, 3 is contained in S. The set 1, 2, 3, 4 is contained in S as well, right? This one is subset, this one's proper subset. Any questions on that? Can you use contains or equals in a proper subset? Well, it's funny that you say that, Jad. So what I'd like to do is use some formal logic to describe, or I should say to define subset and proper subset, okay? So the way that your book says it is a bit like this. A is a subset of B if and only if for all X, if X is an element of A, then X is an element of B. Okay, so that's a subset. So what about a proper subset? So A is a proper subset of B if and only if what? Okay, the first rule of subset and has less elements. Okay, so A is a proper subset of B if and only if A is a subset of B and it has less elements. So how do I say that? And how can I use formal logic to describe the idea that A has less elements than B? Very good. Yeah, that's awesome. Okay, there exists an X, or there exists, maybe I should say a Y. Let me use a different variable. There exists a Y such that Y is an element of B and Y is not an element of A. Yeah? All right, let me close off this bracket. Okay, so everything that's in A has to be in B, and there's something that's in B that's not in A. What do you guys think? For those people that didn't have me last term, are you all happy with this formal logic notation? Questions? Yes, okay. Anyone have any questions for me, wondering what any of these weird symbols mean? Okay. Oh, I'm sorry. Let me go back. What was your question, Jed? I forget. Can you use contains or equals in a proper subset?
Yeah. Like, can we use just contain and equals all the time?
Well, they mean different things, so they're useful in different situations, right? So for example, let me give you an example here of when you would use one instead of the other. Okay, let's talk about set equality. Okay, So let's say A is equal to B. Two sets are equal to each other, right? Well, that's true if and only if what? How could we use what what we're going to do today is we're going to build up a bunch of definitions. Okay, and we're going to use the previous definitions to build up the later ones. So how could I use the idea of subsets to define the notion of equality? Any ideas? Good. A is contained in B and B is contained in A. So I'd say, A is a subset of B and B is a subset of A. But this wouldn't work if I used proper subset, right? So this is not the same thing as A is a proper subset of B and B is a proper subset of A. Why? Why would this not mean the same thing? Okay, good, Natasha. Can you say more? What about the above definition? Yeah, they can't be equal, right? Yeah, that's exactly the part of the above definition, right? You can't have, there has to be something in B that's not in A, right? That's part of the definition of proper subset. I have to have some sort of thing that's in one but not in the other, which means they couldn't be equal, right? Yeah, if they were proper subsets, they'd both have to be smaller than each other. This is always false. There's no such sets where one is smaller than the other and the other smaller than the one. That's impossible, right? You couldn't have both of these things be true. So this statement is a contradiction. It's just always false, right? You can't have, A being smaller than, well, it's as if you said, 4 is less than 5 and 5 is less than 4, right? You can't pick any numbers where this whole thing is true. Right? You could have one side of it be true, but you can't make both things true. You can't have something smaller than one and then the one smaller than the other. It doesn't work, right? And so for that same reason, you couldn't say, 1, 2 is contained in 1, 2, 3, and 1, 2, 3 is contained in 1, 2, because the second part would be false. Yeah, very good. Yeah, it's a great question. Okay, other questions? What else can I help with here? Okay, cool. So let's talk about proving a subset relation. So for example, let's go back up to our set S up here, the set of X in the naturals such that X is between 0 and 5, right? I'll say, okay, I want to show that the set 1, 2, 3 is a subset of the set of X in the naturals such that 0 is less than X less than 5. And I want to prove that. Well, how would I prove that? Any ideas? Okay, we convert to set roster or vice versa. Okay, so so we could put both of them in the same notation. We could put both of them in set roster notation, or we could put both of them in set builder notation. That's an option. Um, I think another thing we could do is we could just use the definition of containment directly, which says for all x, if x is in A, then x is in B. Now, if we wanted to do that, how could we use this definition directly? What would we have to do? Yeah, use each element. So we'll say 1, we'll say let x equal 1. Then 0 is less than 1 is less than 5. That works. X equals 2. 0 is less than 2 is less than 5. X equals 3. 0 is less than 3 is less than 5. We did it. Because we went through all, right, all of the elements on the left-hand side, said, well, the ones that are elements in A, they are in fact elements of B because they meet the rule here, and each of those elements satisfies the rule. So we went through every single one and said, hey, okay, well, they all work, right? Well, let's do a little bit different example. Let's say that we, instead of having one in set roster and one in set builder, let's have a situation where they're both in set builder. I'll take this example from your book here. So we'll say that A is the set of M in the integers such that M equals 6R plus 12 for R in the integers. Set B is N, a set of N integers such that N equals 3S for S in the integers. And I want to show that A is a subset of B. Now, what do you think? Just an English explanation would be great here. Okay, divisibility definition. Okay, so how would that work? Okay, 3 divides A. Well, I guess I would say, for all x in A, 3 divides x. So let me, same idea, but let me be a little bit careful here, right? Because 3 doesn't divide the set itself. 3 divides the elements of the set, right? Okay, which I think is true. And why is that, Andrew? Why would 3 divide the elements of A? Oh, okay, David said it above, I'm sorry. Because you can factor out a 3 from 6R plus 12, right? Since elements of A are of the form 3 times 2R plus 4, right? So you can factor a 3 out of there, which means that all the elements of A are divisible by 3. Okay, good. So what? So what do we do next? Okay, 2r plus 4 is contained in r. Ooh, close. Yeah, we could set s to 2r plus 4. David, let me modify what you said a little bit. I would say 2r plus 4 is contained in the integers, is contained in z, right? Which said another way is the way that Andrew said it, right? Which is that you could take this little s right here, which is some arbitrary integer. You can say, hey, well, you know, that we can just set that to 2r plus 4 and find out whatever r is supposed to be, right? With a little bit of algebra, right? So we would say, Andrew, I like your way of saying it. So we would say, you know, let s equal 2r plus 4 for some r from set A. And from that, we can derive the corresponding s for n in set B. Maybe we should do an example. So let's say that, you know, we have, bless me. So let's say that we had, bless me, m, you know, for example, and that can be our proof, right? I think that's sufficient. Let's do a little example, right? For example, let's say m equals, boy, let's see here. M equals 18, right? If m equals 18, then r equals what? Oh, thanks, Tamara. Yeah, 1, right? So if m equals 18, right, then r would have to be 1, because 6 times 1 is 6 plus 12 is 18, right? So r would equal 1, right? And from that, we can find out what s is supposed to be, right? Well, s is supposed to equal 2 times r plus 4. So s equals 2 times 1 plus 4. S would equal 6, which is actually correct, right? If s is 6, then we'll still get out that 18, right? Which is going to give us the appropriate value for n in our set B. Does that make sense to people? Y'all happy with that? That's just one example, but you know, the algebra will work no matter what the value of r is going to be, right? As long as it's an integer, right? Can't put decimals in there. What about the other way, right? What if I said, you know, is B contained in A, or is B a subset of A? Ideas? Counterexample, very good. It's not. No. And here's a counterexample. Well, here, let me keep this up here so you can see. Okay, so what would be a good counterexample, Andrew? Okay, s equals 1. If s equals 1, then n equals 3, which means that m would have to be 3, which means that r would have to be what? Good, negative 1.5. Negative 1.5, which is not an element of the integers. So that's kind of a crappy z. Let me fix that. There we go. Okay. Negative 1.5 is not an integer, so it would not be an element of A, right? And you can kind of see that here, right? A is all the integers that are divisible by 6, right? B is all the integers that are divisible by 3. So A is a subset of B because the elements that are divisible by 6 are all contained in the set of elements divisible by 3. But it doesn't work in reverse, right? Not all the elements divisible by 3 are contained in the set of elements divisible by 6. And you can see that here because of the non-integer multiplier value, right? Okay, so we would say in conclusion, A is contained in B, but B is not contained in A. So is A equal to B? No, very good, right? The containment goes one way, right? Goes this way, but it doesn't go the other way. The containment has to go both ways for the sets to be equal, right? Okay, any questions about all of that? Does that make sense? While you're thinking of questions, let me say one more thing. Your book makes a big deal about an arbitrary element, right? A particular arbitrary element, which in this case would be X, right? So X here is what your book calls a particular arbitrary element. Right? And the way that you prove things about containment and also about just sets in general is to think about some particular arbitrary element and then use it to show things about the sets, right? So basically, this is what we would usually call a variable, right? So you have some variable, you let it be one of the elements of the sets, and you say, hey, well, if this variable is in this set, does it have to be in the other one, right? X is an element of A. Does that mean it has to be an element of B? And if you have a variable, which could be anything, right? You say, hey, well, for this variable, if it's an A, then it's got to be in B. Well, then you've shown that it's true for everything, right? Because it's an arbitrary element, right? Which means if X is arbitrary, it can vary, it's a variable. And you showed, hey, well, if this variable is in A, it's got to be in B. Then what you've shown is for everything in A, it must be contained in B, right? And the way that it's worked with the counterexample in our next question here was we showed that there was some particular element, right? Not arbitrary anymore. Now we got just a particular element. That's a counterexample of n equals 3. And we said, hey, well, okay, well, for this n equals 3, in that particular example, it's an element of B, but it's not an element of A, right? So to prove a for all, you would use a variable, which your book calls a particular arbitrary element. To disprove something, you just need a counterexample, which would be a number, which would be a particular element, right? So everybody happy with the vocabulary there, particular versus arbitrary versus variable? Any questions on that? Those are not the easiest English words. So any of my ESL folks have any questions there? Okay. Let me know if you do. Let's move on. So next we're going to talk about quite a few more operations that you can do on sets. So far we've talked about subset, proper subset, and equality. Now we're going to do 4 more. Okay. A, U, B. This is called union. And can someone explain what the union of two sets is? A set that has elements from both, okay? So if I was going to describe this as a set, I would say, using a particular arbitrary element, I'd say X is an element of A, X is an element of B, and what's the logical connective I want right here? If I want a set that has elements from both, yeah, good, I want OR, right? This is the OR operator, right? For the union, we could have X's in A or X's from B, okay? What about intersection? What do you guys think? And instead of or, very good. X is an element of A and X is an element of B. Okay, so you can think about these terms, you know, with their usual English meanings. So if you have a union, right, you're in part of a workers' union. So I'm part of a teachers' union. Okay, they're called FAP. Okay, and so that means that I am part of this union that works for, you know, that does things for workers' rights. Okay, and it's not only people that work at PCC that are part of this union, but there are also workers from Portland Public Schools and all over, you know, different educational institutions in Oregon, right? So I could work at PCC, or someone else could work at, you know, Cleveland High School, or, you know, whatever else. Notice I keep saying or, right? And no matter which of those places that I work, you're still part of the union. If you work at PCC or a high school or a kindergarten, doesn't matter, you're all still part of the union. Okay. What about an intersection? Well, usually when we talk about an intersection, we talk about an intersection of streets. Like I could be on the intersection of, you know, 12th and Cooch, right? And if I'm on the intersection of 12th and Cooch, that means I'm on 12th Street and I'm on Cooch Street, right? And I'm on both, right? Because I'm standing in the crosshairs. Yeah. Is everybody happy with that? Any questions? Okay, so they really do mean the same thing as the English words. Okay, so what about set difference? If I say A minus B, that's stupid. I should do complement first. Let's talk about A complement. Now there's lots of C's going on here, which is pretty annoying, right? This is a superscript C, so it's not in the center, it's raised, it's like an exponent, okay? Which is different than the subset C. So we have the subset C, which is short for contains, then we have the superscript C, which is short for complement. And it's not like when you say something nice about someone. That's a compliment. This is a complement, right? So it's not saying something nice about the set, right? What does complement mean? It goes with it. That's true. So yeah, that's right. So like complementary, like you would say, oh, this red wine really complements the roast duck, right? So something that goes well with it. That's the usual English interpretation. And the mathematical interpretation is close to that, but it's not exactly the same in this case, right? So let's say that I had some set of all the numbers, and I'll call that the universe, right? And I have some proper subset of the universe of all numbers called A, right? So the complement is all the elements in U that are not in A. This right here, the shaded section, this right here is A complement. It goes with A. There's A and then there's A complement. And if you take them together, you know, they go with each other, then, and you took their union, then you would have the entire universe. right? So they kind of, you can take that idea of going together and it can kind of means the same thing. It's at least close, right? So, okay. So how would I describe this in terms of my set notation here? So Luan, you were really close to the technical notation, your description there. Good. X belongs to U, but not A. So X is an element of U and X is not an element of A. You could say this a little shorter. This is kind of the same thing as just saying the set of all X that are not in A. But it is helpful to have this idea of a universe, right? Because if I'm talking about, you know, for an example, let's say that I want, remember my set S is the numbers 1, 2, 3, 4, right? And I want to talk about S complement, right? Well, in order to really do that, you know, the all of the numbers that aren't 1, 2, 3, 4, it helps if I know which numbers I'm talking about, right? Am I talking about the natural numbers that are not 1, 2, 3, or 4? Am I talking about the integers that are not 1, 2, 3, or 4? Am I talking about any object that exists in the whole world that's not 1, 2, 3, or 4? Well, that's going to change what S complement is, right? So if I just had naturals, I'd say, well, S complement would be 5, 6, 7, 8, etc. Right? That's for naturals being the universe. Well, what if I had integers being the universe? Well, then I would have, -2, -1, 0, 5, 6, 7, ... and a ... on that side. That's if I had integers as my universe. What if I had anything in the world as my universe? Well, then S complement would include things like, Honda is not 1, 2, 3, or 4, Nick, red, 7, and that set's pretty stupid, right? So I don't really like that set very much. So it is important to the basic idea of the complement is that's all the things that aren't in the set, but it really is important that you include this part about the universe, right? Because otherwise your complementary set is not going to be well defined, right? Is everybody happy with that idea? Any questions there? Okay, so let's talk about one more set difference. This is called difference. And how do you think we might describe this? Using the, well, not XOR, not quite. You're close. Okay, so Sean, you said the elements of A that are not in B. Okay, so to say that in the formal notation, I would say X is an element of A. And Sean, you said that are, so I don't know what connective I want for the English phrase that are, but I'll let you think about that. What about X and B? How would I say that X's are not in B? I have two options, actually. Yeah, okay, so I could strike through the element sign here, right? So I could just put a line through this and that would work. Or I could say X in A, X in B complement. So you guys are both correct. You could say this either way, right? And what logical connective do I want here? what Sean called that R. And, very good. So X is an element of A and X is not an element of B. And another way of saying that, X is an element of A and X is an element of B complement, because these two mean the same thing. Okay, what do you guys think? Looking good so far? All right, cool. All right, so let's do a few examples here, right? Let's say that my set A is the mixed interval from -1 to 0, and B, and what do we got for B here? From 0 to 1. B is the mixed interval from 0 to 1. And I want to find A union B, A intersect B, A complement, B complement, and A minus B. Okay, so let's start with A union B. So that means that an element could come from A or from B. And one more thing to notice, you notice a union is kind of like the symbol for or. It's just curvy instead of pointed. Intersection is kind of like the symbol for and, except it's curvy instead of pointed. Really easy way to remember which symbol's which, right? So Sean, you're close. That's the answer to the next one, actually. That would be intersection. Yeah, it's the open interval from -1 to 1, because it could come from this one or from this one. If it has to come from this one and from this one, then Sean, you're right. For the second question, the and would be only the number 0 is in both. Set difference. Sure. So that set difference here. Something has to be in A, but not in B. Or in other words, in A and not in B. Oh, you want to take a screenshot? Yeah. You got it? Cool. All right. Excellent. Okay. Okay, so what about A complement? How's that going to go? We're gonna need a union in there, right? Because there's going to be two different parts of the complement to A. Yeah, very good, right? But Sean, instead of and, I would say union, right? So I'll say, okay, so from open negative infinity to -1 closed, union, 0 open to infinity open. Very good. Excellent. Okay. Because -1 was not in there, so it is closed in the complement. 0 is in there, so it's not in the complement. Now it's open instead of closed. Okay, how about B complement? Okay, open from negative infinity to 0. Oops, negative infinity to 0. Open, union with 1, which is closed. 1 to infinity open. Cool. Very good. Yeah, great, Andrew. Okay, and how about A minus B? So it's all the things that are in A except for the things that are in B. Awesome, Luan. -1 to 0, open. Very good. All right. Does anyone have any questions there? Okay, let me talk about one more thing, and then we will take a break. So last term we learned about summation. Okay, we said that we had the summation from I equals 1 to n of, let's say, n squared, or sorry, I squared. I always do that, do the wrong letter, I squared, right? So that's going to be equal to 1 squared plus 2 squared plus yada, 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 plus n squared, right? Now this summation notation, we can also do with unions and intersections, okay? And that's if you have a list of indexed sets, okay? So for example, we have sets A0, A1, A2, up to AN, okay? That are all elements of the same universe. In that case, we can describe multiple intersections or multiple unions. I guess I should start out with unions, right? So for unions, we have a union from I equals 0 to n of A sub I, which is going to be equal to A0 union A1 union ... union A sub n, right? So we just have this sort of the sequence where we union together all of the sets in our list, right? Just like up here, we summed together all the numbers in the list. Here we're unioning all the sets in the list. Same basic idea, right? You do the same thing with intersection. So you get the intersection from I equals 0 to n of A sub I, which will be the same thing. A0 intersect, A1 intersect, yada, 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 intersect A sub n. Right, so it's the same basic notation, except instead of the sigma, here we have a big union or a big intersection. And let's maybe do one example before we take a break. So let's see here. What's a good one here? Well, let's take that break and I'll find a good example because the ones in your book chapter are not that great of examples. So I'll look back in the exercise and find you a good one. Let's take 10 minutes because we're halfway through. So we'll take 10, go, please, 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 God, please leave your computer. Go get up, walk around, run up and down the stairs, do some jumping jacks, get a cup of tea, get a snack, whatever you got to do, get some water. Get up, move around, stretch your legs. You need the flow of blood to bring oxygen to your brain so that you can continue to concentrate for another hour and a half. Okay, so please get up, walk around. We'll be back in 10 minutes and we'll do some more math. Sound good? Sounds good. All right. See you guys in a minute. All right. So I found a problem for this union and intersection business. Here's the idea. A sub I is the set of all x in the real numbers such that x is less than I. Okay. Oh, did I do that wrong? Oops, sorry. X is greater than I. Whoa, the other way. Yeah, that's better. X is greater than I. Where I is an element of the naturals. Okay. So, for example, what would be the set of, A sub 5? Any ideas? Very close. It would be the open interval, because this is a strict inequality. So it would be the open interval from 5 to infinity. Very close. Does that make sense, Sean? Yeah, cool. Okay, so let's talk about the open, well, not open. Let's talk about the union from I equals 0 to 10 of a sub I. So what would that look like? You'd have A0, A1, A2, A3, all union together, right? So what would that be? Good. The open interval from 0 to infinity. Okay. How about the intersection from I equals 0 to 10 of a sub I? Well, I think you made a typo, David. Looks like you did. Okay, so that would be the open interval from 1 to 10 closed, like this. Is that what you meant? Okay, not quite. So remember, the intersection means that you have to be in set A0 and A1 and A2 and A3. You have to be in all of them. Not just 10, because these sets can be anything greater than I. There we go, 10 to infinity. So not this one. It would be the open interval from 10 to infinity, which in this case would actually be just A10, right? Does that make sense? So you could have 0 to infinity, 1 to infinity, 2 to infinity, 3 to infinity. But if you have to be in all of them, right? Then if you're the number 4, for example, well, you'd be in the first few. You'd be from 0 to infinity, 1 to infinity, 2 to infinity. You'd be in those, but you wouldn't be in 7 to infinity or 8 to infinity. And you have to be in all of them to be part of the group intersection, right? Okay, so let me ask you something a little bit different. What if I had the union from I equals 0 to infinity of a sub I? What would that be? This one maybe is a little trickier. So it's just equal to A0. Very good. It's just the open interval from 0 to infinity. And can you explain why, David? Well, for questions like these, if it's possible for you guys to use a microphone, that would be really helpful, because we can get through a lot more material and go a lot faster, because you can talk 10 times as fast as you can type. So if I ever, yeah, go right ahead, David.
Because the set includes all a sub I, which has a lower bound of I, which just approaches infinity. So the set a sub I gets smaller as it approaches to infinity, and eventually will just be infinity if that existed.
Sure.
Included in everything.
Yeah, and it could be in any of them, right? Yeah, and Andrew, that's exactly what I was going to say. Each subset each following set is a subset of the last. So the way that I could describe this, I could say A0 contains notice I wrote the C going the other direction, right? Just like I could say 4 is less than 5, and that's the same thing as 5 is greater than 4. I can switch the direction of the inequality. I can also switch the direction of the containment. Okay, so A0 contains A1, which contains A2, which contains yada, yada, yada forever, right? And if you could be in any one of these sets, right? Well, since A0 is the biggest and you're unioning them all together, right? Then you just get A0 at the end of the day. So yeah, that, Andrew, that's a great way of putting it. Is it transitive? Well, yes, containment is transitive in the same way that greater than and less than are transitive. If I have A is less than B and B is less than C, then I can conclude A is less than C. And I can do the same thing with containment. If A is contained in B and B is contained in C, then A is contained in C. Yes, it is transitive. Yeah, good point. So what if I did it the other way, right? What if I instead considered the intersection from I equals 0 to infinity of A sub i's? Now, instead of being in any of them, A0 or A1 or A2, now you have to be in all of them. So what would this be equal to? Excellent, the empty set. Very good. This is the empty set, which you can also denote as a set of curly brackets with nothing inside, right? There can't be anything in there because for each new A that you add, A1, A2, A3, A4, you're eliminating more and more of the real numbers that could be in the set, right? Because if you have to be in A3 as well as 0, 1, and 2, when you list A3 out here, you've eliminated the range from 0 to 2. When you include A4, you've eliminated the range from 0 to 3. So if you go all the way up to infinity, you've eliminated the range from 0 to infinity, which eliminates everything, which leaves you with nothing, which is the empty set, right? So there's a little bit of new notation for you. This circle with a diagonal slash through it, that's called the empty set. Any questions about that? Okay, so let me ask you this. Can you give me another example of set builder notation where the result of that set builder notation is the empty set? So can someone define another version of the empty set for me that's maybe a little bit simpler than this whole situation that we built? Okay, so let me ask you one more time. So what I want is set builder notation. So let me define the universe for you. We'll say the set of natural numbers such that something. So David, I'm not quite sure where you're going with that. A0 complement and A. So let me make that a little bit, let me modify that slightly. Yeah, the intersection, that's exactly right. And we don't even have to use A0. It could be any set you want, right? Some set S intersect S complement. No number can be in a set and the complement of that set, right? Because the complement's all the other stuff. No X can be in both, so that must be the empty set because nothing can be in a set and as well as in its complement. Cool. How about another example? Can you give me another example of set builder notation, which would give me the empty set. So that was a great first example. Okay, A minus A, that's kind of the same thing, right? Because that's saying you have to be an A and so that's sort of a different way of writing a set and its complement intersected. Let me give you a hint. So for something to be the empty set, whatever's in here in the set builder notation has to be false, right? If we took this and interpreted it in logic, we would say, you know, it's some proposition and its opposite, which of course is a contradiction, right? It's false. So anything you put in here that's kind of like false, right? That's going to give you an empty set as the total elements in the set. So can you give me an example of something else that could be false? Maybe you could just use numbers. Any ideas there? Okay, that x is greater than 5 and x is less than 5. That's a great example. Right? There can't be any natural number that's simultaneously bigger than 5 and smaller than 5. Right? Yeah, very good. Okay, cool. So that's a little bit about the empty set. And we're going to use that as we move forward and define a few new objects. So two sets are disjoint. Maybe I should say two sets, you know, A and B are disjoint when A intersect B equals the empty set. Okay, so let's do a couple examples of this. Can someone give me a few examples of two disjoint sets? Okay, negative integers and positive integers. So we could say, you know, A equals the set of x in the integers such that x is greater than 0. B equals the set of integers such that x is less than 0. Then A and B are definitely going to be disjoint, right? Because there will be negatives on one side, positives on the other. Disjoint means no overlap, right? Odds and evens is another great example. Sean, that's another good example. 1, 2, 3, and 4, 5, 6. Those are all perfect. Yeah, very good. Okay, so let's make this a little bit more general, okay? Many sets, A0, A1, A2, yada, 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 are mutually disjoint when for all I and j, if I is not equal to j, then A sub I intersect A sub j is empty. Okay, now can someone explain what this means in English? Or an example. Yeah, none of the sets intersect anywhere. Perfect. That's exactly right. So can someone give me an example of 3 mutually disjoint sets. Very good, Sean. Yep. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. None of those overlap anywhere, except the sets that overlap themselves. That's why we have to start with this part of the conditional. We have to assume that I and j are different subscripts, right? Because, you know, if this is A0, this is A1, and this is A2, well, of course, A0 intersect A0 equals A0, right? Just like in logic, if we had P or P, that just equals P. Sorry, P and P. I wrote the right symbol, but said the wrong word, right? If we have, sorry, one moment, please. My dog's barking at the neighbor. Sorry about that. So in the same way, if we have the intersection of two of the same set, of course, they're just going to equal that same thing, right? Which is not what we're talking about. We're saying any distinct sets are going to have an empty overlapping section, right? If we have the same set, of course, the overlapping section will not be empty. It'll be, 1, 2, 3. So we have to take different ones to intersect them. That's why we're saying I is not equal to j. Any questions about that? Does that look good? Okay. So the last definition in this little run here is a partition. A partition of a set is a collection of sets, a collection of, I should read this, is a collection of subsets where two things happen. Okay, so let's call the set A, and let's call the subsets A0, A1, A2, yada, yada, yada. Okay, so the big set is A, and the subsets are all going to be indexed. Okay, and there's two rules that need to be followed. First of all, A sub I are mutually disjoint. And number two is that the union over all the i's of A sub I equals A. So let me ask you a question. Consider the integers 1 through 10. Can someone give me a partition of the integers 1 through 10 into two subsets? So two subsets, A0 and A1. Okay, 1 through 5, 6 through 10. That one will work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, or we could say A0 is the evens, 2, 4, 6, 8, 10. And A1 is the odds, 1, 3, 5, 7, 9. Okay. Can someone give me a partition of the set A into 4 subsets? A1, A2, oh, I should have started with 0. 0, A1, A2, A3. They don't all have to have the same number of elements. In fact, some of them can even be empty, as a matter of fact, and that would still give you a good partition. Yeah, A and 3 empty sets works. Yep, absolutely. Right. So let me do another one here. Right. I could do A0 equals A, A1, A2 equals A2 equals A3 is empty. Yeah, that works, right? Because if you union all of these together, well, you have a bunch of empty sets union together. Well, nothing with some more nothing still gives you nothing, except for this first one is the whole thing, right? So if you union them all together, you're going to get the whole thing. And of course, these are mutually disjoint, because if something is in one of these things, it can't be in the other, right? Because all of the other ones are empty, right? And the A2 and A3 don't have anything in them to compare in the first place. So they're definitely disjoint. Okay, so that's one possibility. That's a good idea, Sean. What if we wanted to put some things into the sets? Can you give me an example of 4 subset partition of A through 10 with non-empty subsets? Okay, 1, 2, 3 separate. Those are called singleton sets because there's one element inside. Right? So A0, A1, and A2 are all singleton sets. A3 has the rest of A, which would be 4, 5, 6, 7, 8, 9, 10. And the basic idea of a partition, right, is to segment a set, right? Divide it up into parts. That's why it's called a partition, right? So if I had this set 1 through 10, let me make a set here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? I want to divide this up into 4 parts. Well, the way you can think about that is just sort of segmenting the area or dividing up the area into parts. So maybe I could do it like this, right? So there's a part, and there's a part, right? So this partition of A, that would correspond to A0 is 1, 2, 4. The numbers don't have to be in order. I mean, you can put them in order, but you don't have to, right? This would be, so here's A0, A1, A2, and A3. So then A1 would be 3 and 5. A2 would be 7, 8, 9. And A3 would be 6 and 10. Does the idea of a partition make a little bit more sense now? You take a set and you have to use everything in the set, assigning each element to one of the parts. Any questions? Yeah, did that picture help? Hopefully the picture helps a little bit. Your book through in that picture, I think it's a good one. Yeah. Okay. Any other questions on that before we move on? Okay. So two more definitions here. Then we'll be done with 6.1. We can do some practice problems. So first one, is the power set, which is as powerful as it sounds. A little curly P, right? The power set of a set S is the set of all subsets of S. And power set's where it starts to get tricky. Okay, so for example, let's find the power set of the set AB. Okay, now it's going to be a set, right? The answer is going to be a set. I want the set of all subsets of S, not proper subsets, any old subset. Okay, so can someone give me one subset of S? AB, that's a subset. Okay, so AB, that set is included in the power set. Notice now we have a set of sets, which is totally okay. You can have a set of sets, you can have a set of sets, as much nesting of curly braces as you want, just like C++, right? Okay, so what's another subset of the set AB? The empty set. Good. The empty set is a subset of every set. Doesn't matter what we put in here, right? Maybe I should do a little sidebar here. For all sets S in sets, the empty set is contained in S. Why would that be? Well, let's go back to the definition of containment, right? What does it mean to be contained? It means that everything in here is also in here. Well, if there's nothing in here, well, then it's true by default. It's what's called a trivial truth, a trivial case, right? Remember, trivia means that it doesn't matter, right? That's why I hate trivia night, because I never learn a bunch of crap that doesn't matter, like which actor was in which movie. Couldn't possibly care less. So I hate trivia night. Or which sports team won the Super Bowl in 1972. I couldn't possibly care less about that. And the reason why is because it's trivia, and trivia by definition doesn't matter. Okay? So what that means is, in terms of the technical term trivial in mathematics, it means that there's nothing in here that could make it go wrong, right? There's nothing in here that could be missing from S. And so everything in here is part of S because there's nothing that could break it. Does that make sense? People happy with that? So this is called a trivial truth, right? So the empty set is a part of every power set. But we have a couple left. And again, please feel free to interject with questions. I realize I'm going fast today. I will continue to do that for the next 3 months. So please interrupt me if you have questions. So what else do we have in our power set of the set AB? We have the whole set itself. We have the empty set. There's 2 more. Good. The singleton sets A and B. The singleton A and the singleton B. Okay. Let's do another example. Okay. What if I want to find the power set of the set 1, 2, 3? Okay. Let's see if we can list the subsets in increasing order of size. Okay, so we'll start with the smallest subset and we'll stop with the biggest one. So what's the smallest subset of the set 1, 2, 3? Yep, the empty set. Good. Okay. And what comes after that? Well, that'll be the singletons, right? So what are the singleton subsets of 1, 2, and 3? Okay, just the singleton 1, singleton 2, singleton 3. 1, 2, 3. Okay. Next come the 2-element subsets. So what are those going to be? One, 2, 1, 3, and 2, 3. Very good. 1, 3, and 2, 3. And there's one more. The 3-element subset. 1, 2, 3. I'm running out of room here. Sorry about that. Okay, cool. Now here's what I want you to notice. Why is this called the power set? Any ideas? I'm actually going to reorder this so it's in increasing order as well. Empty, A, B, A, B. Yeah, good, because the size of the power set of a set, this absolute value here, that's the size of a set. I guess I should say that somewhere. The absolute value of S is the number of elements in S, right? Okay, so the size of the power set of a set is equal to what? The power of 2, 8, okay. 2 to the number of elements, okay, so you're on the right track. Let's do exactly the right notation. 2 to the exponent what? What should come up here in the exponent? Yes, very good, the size of S. Excellent, right? That's why it's called the power set, because you're finding the power of 2 that corresponds to the size of your set. Notice here we have 2 elements in the set, so we get out 4 elements in the power set. Here we have 3 elements in the set, so we get out 8 elements in the power set. And the pattern goes even further than that. Let's count the number of each different sized subset in the power set. Here we have a 0-element set, there's 1 of them. Here we have 2 singleton sets, pardon me. The singleton sets, we have 2 of them. And here the 2-element set, we have 1 of them. And let's do the same thing down here. The 0-element set, we have 1 of them. The the singleton sets, we have 3 of them. The 2-element sets, we have 3 of them. And the 3-element set, we have 1. See a pattern? Yeah, Pascal's triangle. Very good. Pops up in the funniest places, right? So if you wanted to know how many subsets there are of size 2 in a subset of 3 elements, then what you would do is you would go to Pascal's triangle, right? And find that location on the triangle, which will give you the answer if there will be 3 of them. Right? And we're going to talk a lot more about Pascal's triangle and its relationship to various different parts of mathematics when we go into combinatorics in chapter 9, because we're going to talk about, we're combining the 1, 2, and 3 into different patterns. And we're wondering how many different ways can we combine 1, 2, and 3. So combinatorics is the study of combining things. And it turns out that Pascal's triangle is a huge unifying topic in the study of combinatorics. And we're going to cover that all through chapter 9 in a few weeks here. Yeah. Okay, so that's the power set. Let's do this. Yeah, let's keep moving. Does anyone have any questions about the power set? These examples make sense? Okay, so here's something that I want you guys to think about, just something to keep in the back of your mind, right? We're on Wednesday going to talk about the power set power set of the natural numbers. Okay. Now that's an interesting object because this has an infinite amount of items in it, and I want the set of all subsets of an infinite set, right? And what I'm going to think about is the size of this set versus the size of the natural numbers. So I'll leave that to simmer in the back of your mind until Wednesday and see if you can think about how the sizes of those sets might be the same or different, or how we could determine the size of this power set of an infinite set versus the original infinite set itself. I'll let you all ponder that. This question was studied by George Cantor back in the 1890s. And it forms a huge part of the foundation of mathematics over the past 100 years. So we're going to talk about this quite a bit on Wednesday. Interesting stuff. So well, let's go back to the boring stuff for another minute here. We're almost done. Less boring than the syllabus though, so that's good. Let's talk about the Cartesian product. Okay, and this one really is boring, so apologies, but it's the last one. The Cartesian product of sets A and B. Well, they have a big list of sets here. That's okay, I don't care about that. Of sets A and B is the set of ordered pairs where the first item in the pair, maybe I should say a set of all ordered pairs, where the first item in the pair is an element of A and the second is an element from B. To write this formally, A cross B is equal to the set of ordered pairs A and B such that A is an element of A and B is an element from B. Okay, so let's do an example. So let's say I have, 1, 2, 3 cross AB. So what do you guys think? Six pairs, good. So David, you've picked out an interesting property of the cross product, which is that the size of A cross B is equal to the size of A times the size of B. The reason why we have 6 pairs in this cross product is because we have 3 times 2 total pairs, right? So that's something to bear in mind about the cross product. Good. Let's list them out. So what are my pairs going to be here? Okay, great. So we've got 1A, 1B, and 1C. 2A, 2, oh, I did it wrong. Okay, sorry, 2A, sorry, it helps if you do it right. 2A, 2B, and then 3A and 3B. Very good. You did it right, I did it wrong. and it's a set of all those pairs. Very good. Okay, any questions there? Okay, so your book has an example where you can take a cross product of 3 sets, okay? You can cross more than 2. You can cross as many as you want. So if you cross 3 sets, A cross B cross C, then you would have triples instead of pairs. So let me give you an example here. I'm not gonna write it down because it's gonna take forever. But if we have A1, A2, and A3 crossed together, here's what they are. So here's A1 is XY, A2 is 1, 2, 3, A3 is AB. The size of this set is going to be 2 times 3 times 2, so it'll be 12 total items, right? And these 12 total items are here. We have X1A, X2A, X3A, Y1A, Y2A, Y3A, X1B, X2B, X3B, and et cetera, right? So you list all the different combinations. Again, we're talking combinations here, right? Of one item from A1, the second item from A2, and the third item from A3, right? And any of those combinations altogether will give you 12 total. Yeah? Any questions about a triple cross product? Does that all look okay? All right. The corresponding dimensions on the graph. Yeah, they could, right? So if you want to think about this in terms of graphs, you know, XY coordinate plane style graphs, then what you can think about is, okay, well, the cross product of, you know, something on the x-axis versus something on the y-axis. Well, let's look at it this way, right? So if I had this situation on the x-axis, I have 1, 2, 3. On the y-axis, it's going to be kind of weird, but I'm going to put A and B on there, right? Now, what am I going to have total? Well, I'm going to have 6 intersection points where they're all going to have their own coordinates. So this will be the point 1A, 2A, and 3A. This will be 1B, 2B, and 3B. Right, so this one here would be 3B. I mean, we could do numbers as well on the y-axis instead of letters. I just wanted it to correspond to what I wrote here. Either way is fine. So yes, that definitely does correspond to dimensions on the graph. If we did a triple Cartesian product, it would be a 3-dimensional graph instead of a 2D graph, right? Does that all make sense? Everybody happy? All right, cool. So I could do some practice problems, but I feel like we've done enough practice. Let's jump into 6.2. Maybe we can get a jump start on that before Wednesday. As usual, we're always running short on time in this class, so I'm gonna plow ahead. So let's talk about some properties of sets. So we're getting into section 6.2, and we're going to talk about some subset relations. Okay. So first of all, we have A intersect B is a subset of A, and A intersect B is a subset of B. Okay. A union B contains A, and A union B contains B. And finally, the transitive property, which actually I think somebody mentioned already, A is contained in B and B is contained in C, implies that A is contained in C. Oops, C. Okay. And what I'd like to do is I'd like to demonstrate the truth of these sentences. I'd like to prove them using a Venn diagram. Okay, so we haven't talked about Venn diagrams yet. I think now's a good point to introduce them. So can someone explain to me how I could construct a Venn diagram that demonstrates this first part, not both parts at once, just this first part of my first statement? How could I construct a Venn diagram that would demonstrate that principle? Maybe if you want to hop on the mic and describe in English, that would probably go a bit faster. Okay, fair enough. So does anyone know what a Venn diagram is? Can you just explain what that even means? Intersecting circles. Okay, good. So our sets are going to be represented by circles, and those circles are going to intersect each other. So I think a good way of doing that is like this. So we have some intersecting circles. Here's the set A is the left circle. The set B is the right circle. And this all is living inside of some universe U. That's the universe, is that box around it. Okay. So here's A, here's B. Where's A intersect B? What's that? Which part of the diagram would be A intersect B? The middle, yeah, the little sliver, right? This little part right here, that's A intersect B. Okay. So do you believe me that A intersect B is contained in A? Can you see why that would be? Yes? Okay, why? Can you explain it? It is kind of obvious when you see it, but it's not obvious if you don't see it. And it's always a challenge to explain obvious things. So can someone explain it?
So is it as simple as saying something like all of the area in that sliver is contained in the circle A?
That's it. Yep, perfect. Okay. Yeah, and Luan, you said the same thing, right? This little sliver is contained inside of the circle A. So this is the intersection of the two sets in the middle, and that whole thing lies inside of the circle A. Also, and it lies inside of the circle B, right? Because this little sliver is inside the B circle as well, right? Okay, so let's try the next one. So what about A union B? What would be A union B on this diagram?
Both circles together?
Both circles together. Okay, so I'm going to draw lines going the other way. Okay, so this is A union B, right? And hopefully it's clear that A is inside of A union B because this circle A is inside of both of them together, right? Also, B is inside of both of them together, right? Is everybody happy with that? Any questions? Okay, so we're going to need another different description for this third one, because here we have 3 sets instead of 2 sets. So now we're going to have 3 overlapping circles. And the question is, how do we draw it? Okay, now I want to draw my premise. A is contained in B and B is contained in C. And I want to show that the conclusion is necessary, is required by the premise, by the setup of our, antecedent to the conditional here. Okay, so which circle goes inside of which other circle? So let's start at the beginning. So what goes inside of what? Okay, A goes in B, which goes in C. So here's A. That goes inside of B, right? Because A is contained in B. B then is contained in C. And can you see the conclusion? Then A must be contained in C? Well, of course it is. Here's A, right? and that's contained inside of the big circle C, as long as A has to be inside of B and B inside of C. And that, you know, this again all takes place in some universe U. Yeah? What do you guys think? Does that visual argument make sense? Any questions on that? Si, senor. All right, cool. So let's move on. We can also prove these statements in another way. So this is a proof by diagram, a proof by Venn diagram, but we can also use a proof by elements, okay? So let me do one example of a proof by elements. Let's do this third one, right? So let's do, rather than a visual proof, we'll do a proof by elements. Oops, proof by elements. Okay. So what we're going to do is we're going to start off by saying X is an element of A. What I want to show is that everything inside of A has to be contained in C. Okay, so I'm going to start off with an element of A. Okay, what do I know about the elements of A? According to the premises, they're in B. X is in B since A is contained in B. Right? So if X is in A, then it must be in B since all of A is contained in B. Okay, what do we know next? X is in C. Since B is contained in C. And what can I conclude? Well, I can just combine my previous statements. I can conclude if X is in A, then X is in C, and therefore A is contained in C by definition. There's a proof by elements, right? A very different kind of setup than the visual picture, but of course the meaning is the same, right? So let's try one more. Oh yeah, let's do this one. Okay, this will be great. So let's try another, let's do it both ways. We'll do a proof by elements and a proof by Venn diagram. We'll do it both ways. And this one should make you happy. Okay, so what I want to show is that A union B complement equals A complement intersect B complement. Yeah. So first of all, what law is that? Yeah, De Morgan's law, right? So what we're going to do, again, we have two sets here. So let's build our Venn diagram picture. We have A and B in the universe U. Okay, we want A union B complement. Okay, so where is A union B complement? What would that be? The box without the circles. Good. So everything in the box, not inside the circles, is good. That's going to be A union B quantity complement. Okay, so now let's do the other side. Now we have A complement intersect B complement. Let's take these one at a time. So what's A complement going to be? Everything outside of A. Good. So that's going to be everything outside of A, including B. Okay, so that's A complement. Okay, what about B complement? What's that going to be? Everything outside of B. Good. So that's going to, I'll do that going this direction. Everything, oops, everything outside of B. Okay, that's B complement. And so A complement intersect B complement, that's going to be the crosshatch part, which has these diagonal lines and these diagonal lines. Remember, intersection means and, right? And you can see that the crosshatch section is the same as the pencil section, right? Which means that these two things are equal. So there's a Venn diagram proof of De Morgan's law for sets. Questions? Okay. The intersection would be the middle. Well, no, but that would be the intersection, but that's not the intersection of the complements, right? So you take the complement goes first, and then the intersection happens second. So you take this complement first and this complement first, and then you take the intersection, right? So A complement is everything outside of A. That's the slashes going this direction, negative slope. Everything outside of B is all this stuff. That's the positive slope lines. And to have both, that's the crosshatch part from the pen, right? I probably should have been using highlighters, but it's a bit late for that. I have highlighters. Ooh, I do have highlighters. Sick. Okay, I'll do highlighters on the next one if I need to. Maybe there won't be a next one because we're almost out of time. Cool, you got it. Nice. Okay, so let's do a proof by elements, which is not going to be as fun. Okay. So first of all, what we're trying to prove is that two sets are equal to each other. So for a proof by elements, what are we going to need to show? Two things. For set equality, what two things do we need to show? Both directions of containment, right? So we need to show not only that A union B quantity complement is contained in A complement intersect B complement, we also need to show let me just switch the order this time. A complement intersect B complement is contained inside of quantity A union B complement. So this is a two-part proof. Okay. And for a proof by elements, we start out with an arbitrary particular element on the left-hand side of the containment and show that it must be inside the set on the right-hand side of the containment. So we're going to let X be an element of quantity A union B complement. And what we're going to do is we're going to expand what this means by converting the set symbols into logic symbols. Okay, here's how I'm going to do that. If X is an element of something complement, that means that X, it is not the case that X is an element of A union B. I could have done a strike through the element sign, but I think with the not in front, it's going to be a little bit easier to see. Why don't you guys do the next step? right? This is by definition of complement. Okay, so what do I do next to sort of unpack the set notation and transform it into logic notation? So I already translated the complement. Yeah, I changed union to or. Very good. So I have not x is an element of A inside the parentheses, or x is an element of B by definition of union. Now what do I do? De Morgan's, good. So I can distribute the not over the or. I'll have not x is an element of A and not x element of B by De Morgan's. Okay. Maybe I'll do it this way, just so it's clear. Okay. I should have put the parentheses on the inside, but that's all right. Okay, so if I have, it's not the case that x is an A, now we translate back to the set notation, right? So let's translate the nots first because they're on the inside of the parentheses. So what is this saying? Not x is an element of A. Complement, right? A or x is an element of A complement, and x is an element of B complement by definition of complement. Okay, then the and is going to transform back into intersection, right? So if x is an element of A complement intersect B complement by definition of intersection. And I started off with x is an element of A union B quantity complement. I've finished by saying, well, if that's true, then x must be an element of A complement intersect B complement, which proves what I was trying to show. And I'm going to do the exact same thing in the other direction on this side. So I'll start off, let x be an element of A complement intersect B complement. Okay, well, by definition, what that's going to mean is that it's not the case that x, oh wait, no, I should do the, yeah, I can do that first. It doesn't really matter which direction I do. It's not the case x is an no, it does matter. X is an element of A complement and x is an element of B complement. You have to go outside in, right? You have to do the intersection first. Then we can say it is not the case that x is an element of A, and it's not the case that x is an element of B. Then by De Morgan's, we can factor out the negative, leaving us with x is an element of A or x is an element of B. Transform this back into union. And finally, complement from the negation. What do you guys think? Not as nice as the Venn diagram proof up here. That one's a little prettier, I think. This one's kind of gross, but it works either way. Y'all happy with that? Any questions? Okay, so the last thing that I want to show you is this guy. Remember back in chapter 2 when we had that list of logical identities? Well, now we have a list of set identities, which are those exact same things with the same numbering, the same names, all the same stuff, except now it's just for sets instead of logic. But it's all the same rules that we had back on page, I think it was page 43. Is that what it was? I think it's 43. Nope, it's not 43. Crap. Where is it? the arguments one? It must be section 2.1. There we go. This guy, 35, right? Remember this little box? Hopefully you remember that from last term, right? So that exact same list of logical truths is now reinterpreted here in terms of statements about sets with all the same names, all the same ideas, just a little bit different notation for sets instead of propositional logic. Is everybody happy with that? Any questions there? All right, cool. So that's all I've got for you for today. On Wednesday, we'll finish up 6.2, which I think, yeah, there'll be some good practice, a few practice problems we should do there. And we'll finish up 6.3 and 6.4 and do the lab. So the lab stuff is going to take a little bit because I'm going to show you the whole setup for how to get OpenGL set up and working, and get your, the practice code in there to make sure everyone has that all set up and going. If you took me last term, then it's going to be the same setup that we had last term from OpenGL. It's just going to be a different CPP file that we're going to use. So if you want to make sure that all that stuff is still working from last term, that could be a good thing to do from now till Wednesday. The other things that you should do are read chapter 6 and jump into that web work, 6.1, 2, and 3. And that'll be, if you do the reading, get a start on the web work and make sure that your lab stuff is working right. If you took me last term, I think that would be a good start on some things to do before Wednesday. Does anyone have any questions for me before we go? I'll let you think about it for a minute. Lots of things you could ask questions about. All right, cool. So I will see you at noon for, if you would like to come to office hours. I'll be there at noon on Wednesday, same room, and lecture will start at 1. I'll see you then. Have a good day, everybody. Welcome back to spring term. Yeah, you're welcome, Brian. Have a good one, guys. Yeah, you're welcome. See you later.